Okay, so again, linear transformation we can think of as going from some set of vectors over here to some set of vectors over here. Of course, each of these is going to be regarded as a vector space. So you can just, of course, just any set of vectors, you can't regard it as a vector space. So they've got it like be closed under addition and all that stuff, and the scalar multiplication and everything else. So this is a vector space. This is a vector space. Collection of vectors that satisfies the axioms for a vector space. And here's a set of vectors that does the same thing. And okay. So if we got a vector v1 and a vector v2 in the vector space V, then the vector v1 plus v2 has to be in that vector space. And if we got vector w1 and w2 over in this space, then w1 plus w2 has to be in this space. Now if we've got a linear transformation, okay, transformation is a rule for transforming vectors in this space into this space, or mapping vectors from this space into this space. So let's just say we got a transformation T, then we say that T of V1 would equal W1. And T of V2 equals W2. Okay, that's what these arrows mean. Okay, the arrow from V1 to W1 means that T applied to V1 gives you W1, and the arrow from V2 to W2, that T of V2 equals W2. T takes V2 to W2. Then make the statement that if this and this then T of V1 plus V2 has to equal W1 plus W2, indicated by the arrow that from V1 to V2 over to W1 plus W2. That's one property of a linear transformation. And I should say if T is linear, then if T of V1 equals W1 and so forth, then T of V1 plus V2 equals W1 plus W2. And T of V1 equals C, T of V1 for a scalar C. So that I'm not going to picture that. I'm going to leave the picture the way it is. But these are two conditions. And when these two conditions are satisfied for all vectors in these spaces, in space V, then that's what we mean by the transformation being linear. Okay, it's linear if these conditions are satisfied for every set of vectors in the space. Okay. I'm just going to assert right now that you see why, in doing the homework, you see why it has to be so. for any linear transformation T, and bases, which is basises, and basis, let's say B, B sub V for V, and B sub W for W, let's say if there exists a matrix A such that A multiplied by the vector V expressed as a column vector equals W, where V is expressed with respect to the basis of V, W is expressed with respect to the basis of W, whenever TV equals W. And then we think of this matrix as representing this transformation relative to this basis and this basis. So A is a matrix for T relative to BV and VW. Okay, just going to give you now an example of linear transformation defined by a matrix. Let V equal R3 and W equal R2. Then the matrix A equals 2, 3, negative 1, 1, 4, 2. Defines the transformation T from V to W. Okay? Now this notation T colon V arrow W just indicates that this transformation maps all the vectors in V onto vectors in W. Okay, matrix V equals I don't want to use V1, V2, V2, V3. I'll say A1, A2, A3, then the transformation applied to V equals A times V, which is 2, 3, negative 1, 1, 4, 2, multiplied by the column A1, A2, A3. And that equals 2A1 plus 3A2 minus A3, A1 plus 4A2 plus 2A3. Okay, so that's an example of a matrix of transformation defined by a matrix, where A1, A2, and A3 are just numbers in R3, and these are just numbers in R2. We could also define transformation from R2 to R3. Okay, so let's just do another example, and then we'll ask questions about some of these transformations. Okay, here's a transformation from R2 to R3. And this board's a little wobbly. Oh. That helps. Okay. Okay, defined by this matrix. Let's consider the equation AV equals 0. Okay, well that tells us that 3, 4, negative 1, 2, 2, 6 multiplied by, I've got it backwards, sorry. Need 3 zeros over here, and I only need 2 components here, because we're going from A3 to A2, A2 to A3, R2 to R3, get my letters right. Okay, so we've got A1, A2. Okay, can we solve this equation? Do there exist numbers A1 and A2 that make this true? Well, if we write this out, we see that multiplying the matrix by A1, A2 gives us 3A1 plus 4A2, negative A1 plus 2A2, 2A1 plus 6A2, and that equals 0, 0, 0. Okay, well, is there a solution? Well, yeah, there is a solution. A1 and A2 are both 0. Well, you can see that for any transformation defined by a matrix, if we multiply that matrix by the 0 vector, we're going to get the 0 vector. So there's always a solution. AV equals 0. So I'll say that V equals the 0 vector is a solution. V equals 0 is always a solution to AV equals 0, and that's something that doesn't surprise us a bit. We've known that sort of thing forever. But now if we have our vector space V here, and V is R2, and vector space W here, W being R3, we see that the 0 vector here always maps to the 0 vector over here. Now, is there any other vector that maps to the 0 vector? Okay, well, could we find an A1 and A2 that satisfies all three of these equations? If so, then these three simultaneous equations have to be satisfied. Okay, well, to determine whether they could all be satisfied, we can come back to the matrix and try to row reduce the matrix. Okay, so question is there a non-trivial solution? Well, matrix reduces by Gauss-Jordan reduction to this. You can reduce the matrix and see. Now, it might be that you would have a matrix that didn't reduce to this. Okay, if it didn't, then it would probably reduce to 1, 0, and then 0, 0, 0, 0, we'll see what that means pretty shortly. So from what we've seen earlier in the course, since the matrix reduces down to this, there is no non-trivial solution. Now if the matrix reduced down to 1, 3, 0, 0, 0, 0, what would the equations be? Okay, well the equations could reduce then to A1 plus 3A2 equals 0, and everything else being 0. So we have infinitely many solutions lying along a line and so forth. Well, we'll get to that. Okay, the point is to see what maps to 0. First of all, the 0 vector always maps to 0. Second, we can tell by matrix reduction if there's anything else that does map to 0. Since the matrix reduces to the identity, this tells us that if you apply this to the A1, A2, A3 vector, that A1 is 0, A2 is 0. Okay, so the only solution is the vector v equals 0. Little terminology. If AV equals 0, then V is in the kernel. With a transformation. Kernel is a set of vectors that map to the 0 vector. So in general, then we're no longer talking about this example, but in general, you have your vector space V, and these can be any vector spaces now, and your vector space W, and you have the 0 vector here, and you have the 0 vector of W, and one maps to the other. Well, there's some subspace of V that maps to the 0 vector. In this case, that subspace is just the 0 vector. But in other cases, you could have a whole bunch of vectors here that map to the 0 vector over here. So all the vectors here map to 0 vector over here. All the vectors map in the kernel. All the vectors in the kernel map to the 0 vector, and no vectors outside. I'll say only vectors. In the kernel map to 0 vector. Okay, so the kernel is all the vectors in V that map to the 0 vector. Just looking to see if I have room. I have limited board space available with tests coming up, exams coming up. I used a lot of board space earlier and haven't had a chance to clear it, so I'm going to have to use this little space over here. Okay, so here's another example. Okay, now notice that my third row is the sum of the first two. So okay, I'm going to have to reduce this. Should have made one that's easier to reduce in my head. Okay, A reduces. We're going to get 1, 2, 1, just bringing this up to this row. And I'm not going to explain the process of reduction. And then we're going to subtract this from the second one, giving us 1, negative 1, negative 2. And I'm just going to put a line down here because the third row is clearly going to reduce to the 0 vector. Matter of fact, I can just do that 0, 0, 0 because I can subtract, well, I can subtract the sum of these two rows from this one. It's going to give me 0. If you understand the reduction process, that's pretty straightforward. Okay, so we have this. A reduces to this. And I don't know why I reduced to that. Okay, reduces to 1, 2, 1 up here. Then subtract 2 times this from the other. You're going to get 0 and negative 3 and okay, I'm looking at it blind. 2 times 1 minus this. This minus 2 times this is 0. This minus 2 times this is minus 3. Yeah, that is minus 3. Okay. So that reduces to 1, 2, 1, 0, 1, 1, 0, 0, 0. Get in trouble when I try to shortcut things. And that reduces to 1, 0, negative 1, 0, 1, 1, 0, 0, 0. So there's a reduction of this thing. Okay, so AV equals 0 if what? Okay, now this is again something we've done much earlier in the course. If V is like X, Y, Z, then X has to equal Z and Y has to equal negative Z. So we could express V as T, negative T, t which is t times 1, negative 1, 1. And that works, and that works, and that works, yeah. If you multiply this matrix by 1, negative 1, 1, you get 0. Okay, so I need some extra words. I don't have to say it, but I will. Kernel of transformation defined by A is the span of the set that I'll write as a vector in this form, the span of the set 1, negative 1, 1. Okay, so now if A is the defining transformation here, then the vectors that go in the kernel and map to 0 are the multiples of 1, negative 1, 1. Now one possible multiple is the 0 vector. 0 times 1, negative 1, 1 is the 0 vector. But any other multiple of 1, negative 1, 1 is in the kernel. Okay, well, if B is just plain old R3, then the multiples of 1, negative 1, 1 are represented by the vectors that go through the origin and are multiples of the vector 1, if x is 1, negative 1, y is negative 1, and z is 1, vectors in this direction. So the kernel would be identified with a line through the origin parallel to this vector. Now we're going to go on and talk about that a little bit because the geometry of this thing helps us get a handle on it. The whole idea of kernel, rank, nullity, etc. And that's what we're leading up to because that's going to be in the assignment soon. Okay, so I'm going to turn the camera off for a second and then continue.